This video is FIN1033, Fundamentals of Financial Planning, and today we're going to be looking at Chapter 2, which is the time value money, and we're going to start to learn how to use the financial calculator. The time value of money, the arithmetic of finance. So the learning objectives for this video is to master completely the mechanics of time value of money calculations, to understand the concept of a rate of return over one in many periods, and to understand the different factors affecting rate of return. This slide is looking at what is a discount rate. So a discount rate equates value of cash flows received or paid at different times. Discount rate also assumes different forms of cash flow are pure substitutes if properly discounted. This next point is an important one. The discount rate is the best alternative available investment, and the opportunity cost finally is what you gave up for it. So for example, if I have an investment that is offering me 8%, but there's another investment that I could maybe do that's worth 10%, and I do the 8% and not the 10%, then the opportunity cost would be the 10%. That's what I gave up, okay? Some of the things that we're going to be looking at throughout this presentation on the time value of money are future and present values, both single period and multi-period, which we call annuities. We're also going to learn to use a financial calculator. There's 5 function buttons across here. N, the number of periods. IY is the discount rate. PV is present value. PMT is payment. And FV is future value. So we're going to learn how to use the financial calculator. This is the Texas Instruments BA2. What I'm showing you is the professional. You might have something in your hand that looks a little bit different. It could be the BA2 Plus. It could be an older model. Anyhow, the keys will all be in the same place, okay? And we're going to look at annuity due and deferred or ordinary annuity, and we're going to look at growing annuities. When we head into multi-period rates of return, we're going to be looking at arithmetic rates of return, geometric rates of return, which are very important when you're studying finance. We're going to look at understand what the annual percentage rate is, the effective annual rate, and the reinvestment rate assumption, how that factors into our calculations. Okay, now we're going to jump into some time value of money examples, and the first one that we're going to look at is how to calculate the future value. So the first thing that we're going to do is we're going to look at the algebraic formula for future value. And future value equals the present value times 1 plus the interest rate or discount rate to the power of n. In this case, n is the number of years. So the first example that we're going to look at is if I invest $100 in a GIC for 5 years at 4%, how much is it worth in 5 years? So for those of you that don't even need a financial calculator, you could do $100 times 1 plus the interest rate, which is 1.04. And if we did that 5 times 1.04 times 1.04, etc., 5 times, you would get the answer to be 121.665. Okay, so that's the easy way. Let's start always with the simplest way. Start with $100, 4% for 1 year, 4% the second year, 4% for third year, 4% for the fourth year, earn 4% for the fifth year. So 100 times 1.04 times 1.04 times 1.04, and we do that 5 times. Okay, so but if I bring up the financial calculator and use the algebra, how else can we do it? So let's just follow it. So it's 1 plus the interest rate. So 1 plus 0.04, that's 4%, gives us 1.04. We're going to do y to the x for 5 years, and we're going to multiply that times our $100 present value, and we get 121.665. Okay, now we know that we also have this functionality across the calculator where n is the number of years, IY is the discount rate, 4%, PV is the present value, payment is the payments. In this case, there's no payments, just the initial value. And then we can calculate the future value. Now, one thing we also have here, you see a second functionality, PY, that's the number periods per year. If it's semi-annual, PY would equal 2. If it was quarterly, PY would equal 4. If it was daily, PY would equal 365. So we always want to check second, check the PY, and that we're set to 1 because there's no semi-annual or quarterly payments in this case, okay? So just going to show you, and the other thing to note is that for present value and future value, we're talking about cash flows. So if I'm taking $100 and investing it out of my pocket, we're going to use a negative sign because for the calculator to work perfectly, we need one present value to be either a negative or a positive sign. Okay, so let's just do that. So we're going to do $100 is our, I'm going to, out of our pocket, negative is our present value. We're going to do 5N, which is the 5 years. We're going to do 4% is the interest rate. There's no payments, just the initial cash flow out of our pocket. And then we're going to hit compute the future value, and we get the 121.66. Okay, so that's a couple of different ways of calculating the future value. Okay, on this slide now we're going to look at how we calculate the present value. So recall on the previous slide we're calculating the future value, and it was equal to the present value times 1 plus the interest rate to the power of n. Okay, so you can see if we want to calculate the present value, what we would do is we would just divide this side divided by 1 plus k to the n, and divide the other side by 1 plus k to the n, and that would isolate the present value. So present value, just a bit of rearranging, equals the future value divided by 1 plus k to the n. So that's just a little bit of algebraic rearranging. Now you can see here that some students might find that to be a little bit confusing. We could also write that as present value equals the future value times 1 plus k to the negative n, using a negative power. But I find that a little bit confusing, so I think it's easier just to go with this formula. Future value equals present value times 1 plus k to the n, so the present value equals the future value divided by 1 plus k to the n. So in this example that we're going to look at, I promised to give you $100 in 5 years, so that's $100 coming into my pocket in 5 years. We're going to make that a positive sign. The discount rate is 6%. How much is the promise worth today? Okay, so if I bring up the calculator here, we're going to have $100 is the future value. There's no interim payments at all. The interest rate is 6%, so that's 6 IY, and it's for 5 years, so it's 5N, and I'm going to hit compute the present value, and the present value, you can see that's a negative. In this case, they put the future value as a negative, and the present value came as a positive. I put the future values as a positive because I said it's going to come into my pocket in 5 years, so it's giving me the solution in the negative. Again, that just reinforces the fact that one number has to be negative and the other has to be positive. Okay, so that's how we could also calculate it using the algebra. But again, I think once you start to understand how to use the financial calculator, you're going to find a lot quicker and easier to use. But different strokes for different folks. I've had many students that love algebra, and others like to use the calculator. Anyhow, if we're doing it with the algebra, just to show you very quickly, it'd be the present value equals that $100 divided by 1.06 to the power of 5. Okay, I'll let you finish that off yourself. Okay, this slide now we're going to look at the future value of an annuity, and this is deferred, which means that the payments are coming at the end of the year. So let's just jump in and look at the example here. It says if I deposit $100 into an account paying 2% per annum at the end of each year for 3 years, how much do I have in 3 years? So let's draw the timeline. So at time 0 here, we're not making any deposit. At the end of year 1, we're going to put in $100. So that's out of our pocket. We make a negative sign. That's at the end of year 1. At the end of year 2, we're also going to make another deposit, $100. And at the end of year 3, we're going to make a deposit of $100. And we want to know what is the amount at the end of the 3 years. Okay. So if I bring up my financial calculator, you're going to see that using the calculator is a lot easier than doing the algebra in this case. So again, I'll always just check my periods per year that it's at 1. It's not semi-annual. And so let's just run through it. So you can see here at time 0, the present value is 0. Okay, so let's just bring up the calculator. We're going to do 0 present value. The payment is going to be $100, and I'm making that a negative because it's out of my pocket. Okay, we know the interest rate is 2%, so 2 IY, and it's for 3 years, so 3N. And then simply we're going to compute the future value, and we've got 306.04, and that's the correct answer there, 306.04. Okay, now we're going to be looking at the present value of an annuity deferred. So in this example, it says I win a prize, $100,000 paid at each year end for 20 years. And we want to know how much is it worth today at my discount rate of 3%. So it's a present value question. So let's bring up the financial calculator again. And let's start from the right-hand side and work our way back to the left. So we're going to get 100,000 paid each year for 20 years. That means at the end, we're going to have a zero future value. Okay, that's a little bit of a trick that you have to kind of think your way through. And you see, you're going to get $100,000, and that's cash into my pocket each year for 20 years. So we'll keep that as a positive. And we're going to make 100,000 is our payment because we're going to get 100,000 each year for 20 years. Okay, we're going to calculate the present value, what it's worth. So the interest rate is 3%, so it's going to be 3 IY, and the number of years is 20, so 20N, and we simply hit compute present value, and we get 1,487,747 and 49 cents because it's a bit of rounding. Okay, again, in this case, much easier to use the financial calculator than working your way through the algebra. Okay, now in this case, we're going to look at what's called an annuity due. And what is the difference between an ordinary annuity and annuity due? It's just simply the timing of the cash flow. With an ordinary annuity, the example that we saw in the previous one, we're getting all our cash flows at the end of the year. Now, an annuity due, the cash flow happens at the beginning of the year, and that's the only difference. So in this case, it says I win a prize, 100,000 paid at the start of each year for 20 years. How much is it worth at 3%? Okay, so what they're doing in this case, it says that a quick way to do it is to just take the calculation that you did on the previous slide and then multiply it by 1.03 because it's happening at the beginning of the year. Okay, but I like to show how it's done on the financial calculator. So again, there was the answer from the previous slide, but that was from an ordinary annuity when the cash flows were coming from the end of the year. To change it to the beginning of the year, what we want to do is it's very simple. We can see there's a second functionality here. It says begin. So we do second, begin, and then we do second, enter. Okay, and then we hit clear. And now we can see this BGN, the calculator is in the beginning mode. And I prefer to use the calculator properly and just change the presets. So now if we do the same entries, 0 is our future value, and we're getting 100,000 a year for 20 years. So I type in 100,000, oops, one too many zeros, and it's money into my pocket, so I'm using it as a positive sign. That's my payment. And the interest rate is 3%, so 3 IY, and 20 is the number of years, 20N. And we hit compute present value, and we can see we've got 1,532,379, and in this case, 91 cents. Okay, so again, I recommend that we change the calculator into the beginning mode for an annuity due where the cash flow is happening at the start of the year. Again, to change it back, we do second, begin, second, enter, we hit clear, and you can see here the calculator is in the ending mode because I don't have anything showing up on the screen. To change it to beginning mode, second, begin, second, enter, and there we're now in the beginning mode. Now we're looking at rates of return, and we're going to compare arithmetic versus geometric means or averages. Okay, so we've got 5 years of returns. In year 1, we've got return of 4%, year 2, 8%, year 3, 6%. Year 4, we've got negative 2% return, and in year 5, we have a 5% return. So to calculate the arithmetic mean, and mean just means average, so the arithmetic average is just the sum of the numbers divided by the count of the numbers, and it gives us 4.2%. So that's pretty easy. 4 plus 8 plus 6 minus 2 plus 5 gives us 21 divided by 5, and that gives us a arithmetic average of 4.2%. But the geometric mean is important because we use it when we're looking at financial returns, and I'm going to have a couple of slides on that next to show you why it's important to understand it. So the formula is 1 plus the rate of return times 1 plus the rate of return for each of the years to the power of 1 divided by n, which is in this case 5, and then we do minus 1. And to get it back to the whole number, we can multiply it by 100. Anyhow, let's just do it on the calculator. You'll see. So it's 1.04 times 1.08 times 1.06. And then, of course, 1 plus negative 2% is 0.98 times 1.05. And that gives us 1.22512. We do y to the x to 0.2. That's 1 divided by 5. And we get 1.0411. It's showing here negative 1. And if we multiply it by 100, we're going to see that we've got 4.1434, 4.14%. So the geometric mean is also called the compounded annual rate of return. It's very important when we're looking at financial returns. So I just wanted to work through an example on geometric mean and show you why it's important when we're looking at financial returns. So when we're looking at historical returns on investments, we want to use geometric average. In this example, we'll quickly show you why. So in this example, we're going to start with 10,000 US dollars, and we had the following returns for 4 years. Plus 10% in the first year, minus 25% in the second year, plus 21% in the third year, and plus 6% in the fourth year. So the arithmetic average return is 3%. So that's easy. It's 10% minus 25 plus 21 plus 6 divided by 4. So just bring up the calculator again just to prove that. So we have 10 minus 25 plus 21 and plus 6. And we're going to divide that by 4. So we get the arithmetic mean, or the average, of 3%. Okay? So if we looked at that and we calculated the 10%, times 1.03 times 1.03 times 1.03 times 1.03, we get a total of $11,255.08. But that is not what our actual balance would be. And that's why we don't use arithmetic averages when we're looking at financial returns where there's variability, and in particular negative returns. So let's just look through it. If we have $10,000 at the beginning, and we earn 10% in the first year, we'd have $11,000 at the end of year 1. Then that $11,000 times the negative 25%, we'd have $8,250 at the end of year 2. $8,250 at the beginning of year 3 times 21% in year 3 return, we'd have $9,982.50 at the end of year 3. So at the beginning of year 4, we take that amount, multiply it by 6% for year 4, and actually our balance at the end of year 4 is correctly $10,581.45. That's what we have, not the $11,255.08 that we calculated using the arithmetic mean or average. Okay, so again, going back to the formula for the geometric mean, it's 1 plus the return year 1 times 1 plus the return in year 2, and we continue that on, and we put it to the power of 1 divided by the n minus 1 times 100 to get it back into the whole number. So again, we had 10% return in year 1, negative 25% return in year 2, 21% return in year 3, 6% in year 4. So the to calculate the geometric average, it's 1.1 times 0.75 times 1.21 times 1.06 to the power of 1 divided by 4 minus 1 times 100. So if I just bring up the calculator here, we can do it very quickly. It's going to be 1.1 times 0.75 times 1.21 times 1.06. It's going to give us an equals. We're going to do y to the x. 1 divided by 4 is 0.25. Don't need my calculator for that. I'm going to do equals minus 1 and times 100 to get it back into a nice round number. And it's 1.42296%. So we can see that's considerably less than the 3%. So when we have variabilities in returns, and in particular negative returns, the geometric average is always going to be less than the arithmetic average. Now, I'm not going to bring up the calculator to do it again, but just to show you then the simple way, the $10,000 times the 1.0142296 over 4 years for the average, and that's going to give us the correct balance in the account at the end of the 4 years. Okay, so that is the correct balance in the account after 4 years. Using the geometric average adjusts for the fact that after a negative year, there is less balance in the account on which to apply the following year's returns. So it's important not to use arithmetic averages when looking at average annual investment returns. So I hope this example has helped you understand why the importance of the geometric mean and using the geometric averages. The next thing we're going to look at is the effective annual rate. And the effective annual rate is when we're looking at when the compounding period isn't for a year, but it could be less than a year, like, for example, semi-annually, in which case you'd be compounding twice per year. Okay, so here we have an algebraic formula to calculate the effective annual rate is 1 plus the interest rate divided by m, and that's the number of compounding periods per year, to the power of mn, which is the number of compounding periods per year, times the number of years, minus 1 times 100. Okay, so let's just look at the example. You invest in $100 in a bond that pays you 6%, but that's compounded twice per year. Okay, so the nominal interest rate is the 6%. That's the stated interest rate or the annual interest rate. But the interest rate per period is 6% divided by 2 because it's twice per year, semi-annual. So you get 3%. So the easy way, as I always say, start with the easiest way. It's $100 that you invested in. You're going to get 3% in the first 6 months and 3% in the second 6 months. And that's going to give you $106.06 at the end of the year. $100 times 1.03 times 1.03 gives you 106.06. Okay, but if we look at what the effective annual rate, so 6% was stated as the annual rate, but it's compounded twice per year. So we do ending minus beginning divided by beginning times 100%, and we get an effective annual rate of 6.09%. That's just our rate of return. Remember, it's ending minus beginning divided by beginning, and that gives us our holding period return. Okay, so the interest earned in the first 6 months, 100 times 6% divided by 2 is $3. You have $103 times 3% again, and that's going to give you $3.09. That gives you your interest earned of $6.09 for that year. On this slide, we're going to work through the effective annual rate using both the algebra, but then I'm going to show a tip that you can use on the calculator using some functionality on the financial calculator. So again, the algebraic formula to calculate effective annual rate equals 1 plus the interest rate divided by the periods per year, in this case semi-annual, so that's 2, m equals 2, to the power of mn. M again is the periods per year, 2, and n is the number of years. In this case, it's 1. 6% compounded semi-annually for 1 year. So let's just bring up the financial calculator again, and we'll just work it through the algebra. So the way I always start is 0.06 divided by 2, and then we're going to hit plus 1. So it's 1.03 gives us our the amount for within the brackets. Y to the x to the 2 minus 1 and times 100 to put it in a nice round number, and we get 6.09%. Okay, but so that's the effective annual rate when it's 6% compounded semi-annually. But we can use the financial calculator here. We have a second functionality above the number 2 key. You can see ICONV, that means interest rate conversion. So to calculate from an annual rate to an effective annual rate, if the compounding periods is less than 1 year, we can use this calculator functionality. So second, interest rate conversion, NOM equals the nominal rate. We're going to do 6%, and we're going to hit enter. Then we're going to arrow up, and CY is the compounding periods per year. That's 2 because it's semi-annually. We're going to hit enter. We're going to arrow up again. It says effective. We're going to hit compute, 6.09. So it's easy to calculate the effective rate using the interest rate conversion. Again, if I'm going to clear the calculator, second interest rate conversion, I can clear the work that's in there if I've done a previous question by doing second clear work. You see here, clear work above the CE key. So now it's back to 0. So just to do it one more time very quickly, nominal rate 6, enter, arrow up, compound periods per 2, enter, arrow up, compute the effective rate 6.09. Okay, very easy to use the financial calculator to calculate effective annual rates. Next thing I want to do in this video is just quickly scroll through the notes. A lot of the calculations you can use the notes to practice because we've shown throughout the PowerPoint slides how to do quite a bit of this. So Personal Finance Chapter 2, Time Value Money, we can see the learning objectives is to master the mechanics of time value money. So very quickly, the notes first looks at the rate of return for a single period. And the algebra here is cash flow 1 at time 1 minus cash flow at time 0, that's today, divided by cash flow today. Or the way that I like to simplify it is just to say ending cash flow minus beginning cash flow divided by beginning cash flow. So in the example here, you're going to get $1,000 1 year from now, but you have to invest $909.09 today. What is the rate of return? So it's ending minus beginning divided by beginning. We get a 10% rate of return. Next thing the notes takes you through is the opportunity cost. We talked about that in the slides. Then we're looking at compounding more frequently than annually and how to calculate the effective annual rate. And the example here in the notes is looking at a credit card that charges an annual rate of 19%, but it's compounded monthly. So how do we calculate the effective annual rate? Well, we'll do that again on the calculator just to be sure. Okay, so I'll bring up the calculator here, and we know we can use the interest rate conversion functionality. So the nominal rate is 19% on that credit card. I'm going to hit enter, arrow up. It's compounded monthly, so that's going to be CY equals 12, enter, arrow up. And to get the effective annual rate, we're just going to hit the CPT compute, and it gives us an effective annual rate 20.74510, correct, 20.745, and my calculator is 10. Okay. Scrolling down through the notes now, we can see that it just goes through the future value, algebra, and a simple example. I'll let you work through that on your own. Present value gives the algebra and a simple example using the calculator. I'll let you work through that. And there's something here now talking about inflation and the rule of 72. This is kind of important. What is the rule of 72? It says this is a simple rule of thumb and is used to estimate the effects of inflation. Take the number 72 and divide it by the rate of inflation, and it'll show you how many years it takes until your money either doubles for the discount rate or is worth half as much. So in this example, you've got $1 million. There's 3% annual inflation. It would be worth about $500,000 in 24 years. 72, the rule of 72, divided by 3, that's the inflation rate, equals 24. So your purchasing power in 24 years would be about half as much, okay? So scrolling through the notes a little bit more, we can see here then it's talking about the Fisher equation, and that's, you can see here, KR is the rate of return adjusted for inflation. It equals 1 plus the nominal rate of return divided by 1 plus the rate of inflation minus 1, okay? So, and this gives you a bit of an example. Then it's scrolling through a little bit about income tax. We like to look at, when we're looking at financial figures, we like to look at things in after-tax dollars. So how do we do it? We take the, we always take the amount times 1 minus the tax rate, and that gives you your after-tax dollars. And then it scrolls into some of the notes with regards to Chapter 4. Okay, but I'll let you review the notes on the Blackboard yourself. Just going to end this video with a quick navigation of the Blackboard. So here we are in the Blackboard, Fundamentals of Financial Planning. So of course we've got the course content. If we click on that, we can see that we've got the class notes, the course outline, review materials, time value money, self-study case, which we'll look at later. And then, of course, we get into the assessments. And in this case, we've got online test number 1, based on the CFP Code of Ethics, which is Chapter 1, Time Value of Money. So just going to do one time value money question with you as a bonus for watching the video. You can see here, question 3, Rita and Eric have an annual spending plan that amounts to $36,000. That's in today's dollars. If inflation is 5% a year for the next 3 years, what amount will they need for their living expenses 3 years from now? Okay, so we can bring up the financial calculator, and we're going to use this functionality. So we can see that their current spending needs is $36,000 in today's dollars. So we're going to make that the present value. There's no interim payments. The interest rate or inflation rate is 5%, and it's for 3 years. So that's 3N. We're going to compute the future value. We can see it's 41,674.5. So the correct answer is A, 41,675. Okay, because it's just been rounded up. And that's the end of this video. Thank you very much.